Okay, good afternoon to you. My name is Emmanuel. I'm here to um, introduce the kinetics of fluid particle reaction. And this topic is under the course Chemical Reaction Engineering 3. And it is the course code here in photo, Chemical Engineering Department is CHE 512. CHE 512. So we're looking at introduction to um, fluid particle reaction. Introduction to fluid particle reaction. So in the course of this class, and I want you to permit me to refer to my notes as we journey together. Okay, so CHE, is it necessary? No. Let's just write the topic. The topic remains. Let's do it this way. Introduction to kinetics of fluid particle reaction. Kinetics. Introduction to kinetics of fluid particle reaction. Now, the topic kinetics of fluid particle reaction is concerned with basically the derivation of the kinetics of heterogeneous reaction. Now, this heterogeneous reaction, of course, you can still remember the differences between or different types of reaction, homogeneous reaction and heterogeneous reaction. Now, homogeneous is the ones that are the reactants are in the same phase. Okay, I'm talking about non-catalytic homogeneous and the heterogeneous reactions. So the reactants are the same phase, and the heterogeneous reactions or non-catalytic heterogeneous reactions have to do with the reactions in which the reactants are in different phase. When I talk about phase, I mean the solid, the liquid, and gaseous phase. Now, the introduction to kinetics of fluid particle reaction or kinetics of fluid particle reaction has to do with heterogeneous reaction. That is the derivation of the kinetics of heterogeneous reaction. And then in this heterogeneous reaction, gas or liquid, which we can generally refer to as fluid, contact with a solid. Okay, gas or liquid, which we can refer to fluid, contact with a solid, react with this solid, and then transform the solid into products. Okay, so we are principally looking at the derivation of the kinetics or the rate equations of a heterogeneous reaction in which fluid contact with solid, reacts with it, and then transforms it into what? Products. Now, such reaction can be represented thus: fluid reacting with solid to give products. Now, we can use some denotations, okay, to denote fluid, solid, and products. Now, mind you, under this kinetics of fluid particle reaction, okay, we are concerned with solid products. Now, the fluids can be denoted with A or by A, plus the solid can be denoted with capital B. Okay, now the A here is assumed to be in enough quantity. You get, the A is not the limiting reactant per se. Now the solid is the limiting reactant, so it has a definite mole, okay, which is small letter b. So A in sufficient amount reacting with B moles of capital letter B to give us a solid product. We are concerned principally with a solid product or solid products. Okay, now we have so many instances this type of reactions have so many uses in the industrial setting and all of that. For example, the roasting of sulfide oils to produce metal oxide, among other examples. Okay, now this is the basic denotation. Okay, which we can refer to this as equation 1 and then this as equation 2. Now this is the basic denotation of what, or the equation of reaction that we are concerned with under kinetics of fluid particle reaction. Kinetic of fluid particle reaction. Remember that these reactions are non-catalytic reactions. These reactions are what? Are non-catalytic reactions. Okay, now it is vital to note that these solid products either remains unchanged in size. Okay, now this solid product formed either remains unchanged in size, okay, during and after the reaction, containing impurities which remain as a non-flaking ash. Now, two things must happen to these our solid products, or two things must our solid products can, that's the solid product, the appearance or solid product formation, okay, can be in two, can I call it two condition. Our solid product can be in two conditions. I think that's the best word to use. Okay, number one is that it is either it remains unchanged in size or it changes in size. Now, how does it remain unchanged in size? By containing impurities. What are these impurities? Impurities are particles that are left by the reaction or the byproduct of the reaction. Now, this solid product can remain unchanged when it contains impurities in form of non-flaking, ash. Now, we refer to these impurities as ash. Now, when the ash is in form of non-flaking, what do we mean by flaking? Flaking has to do with breaking away. Now, when the ash are not breaking away from the particle undergoing the reaction, then you will notice that the solid product, okay, the solid product, that is the product of the reaction, will remain unchanged in size. This is what we mean. Now, if we have a solid particle, okay, and then it undergoes reaction, and then let's say that after reaction or after time T, okay, now all these places have underwent reaction. Are we together? Yes. All these places have underwent reaction. Okay, so if this impurity or leftover of the reaction, if they break away from this solid particle, you will notice that the solid particle or the solid product, okay, the solid product will reduce in size. Okay, you see that we can say that the solid product has changed in size during the reaction. Okay, during the reaction. Now, but when these impurities, or we can refer to them as ash, when they are non-flaking, okay, that is when they don't detach themselves from the surface of the unreacted core or within themselves, that is within the particles that make up the ash, when they don't detach from the unreacted core, then you will notice that the solid product will remain unchanged in size. Okay, so that's why I have it here that solid product, this solid product consigned here either remains unchanged in size, okay, now during the reaction, containing impurities which will remain as non-flaking ash, okay, or the solid product changes in size. Okay, now this is an instance of the solid product not changing in size. This is unchanging size. Okay, so let's look at a scenario when it changes in size. Now, when it changes in size, let's assume that this is what? Now, when it changes in size, generally it contains, the impurities are flaking ash. Flaking ash. Okay, let's assume that this is our particle. Let's assume that this is our particle. Now, after the reaction or during the reaction at time t, let's assume that this area has underwent reaction. Okay, this area is now the impurity or the leftover, okay, of the reaction. Now, when this area now starts to detach, that is when it starts to fall off. When it starts to fall off, okay, when they start to fall off from this unreacted core, that is the ones that are still going to undergo reaction. Okay, when they will start to fall off, you see that the size will keep reducing. Okay, the size will keep reducing. It will not be the initial size. It will not be what the initial size. It will not maintain its size. So this, when this what's it called, the flaking ash, when they start to break away from this unreacted core, okay, so in that condition we call it what, changing size. We say that the solid, that is the solid product, has a what, a changing size. Okay, this is very important. You understand that in as much as we are looking at fluid reacting with solid, that is reacting with B moles of capital B, where capital B is the solid. Now this is the fluid. This is the fluid, which can be gas or liquid. Then this particular B, this capital B is the solid. Okay, this small b is the mole. The small b is the mole of what? Of the capital B. Now, in as much as we are considering fluid reacting with some mole of solid to give us solid products, these solid products can either be of unchanging size when the impurities are in form of non-flaking ash, or changing size when the impurities are flaking ash. Gotten? Okay. If you have any question, you can drop it in the comment section. Get? Okay. You can drop it and drop it there. Now, aside that, okay, this point is very important. Now let us look at the selection of reaction model. Now when we talk about a model, okay, model is what aids design, okay. It's not design in itself, okay, but we can refer to it as design, but when we talk about model, we're talking about a conceptual picture. A conceptual picture, okay, with its mathematical representation. A conceptual picture, or something that we can visualize about a particular process, and then we can now design it, that is, derive its mathematical representation. Now when we talk about this heterogeneous reaction, that is the fluid particle reaction, so we have two predominant reaction models. Okay, we have two predominant reaction models. Now, but before we look at the models, let's look at the criteria that makes for the selection of a good or a relatively excellent model. Okay, now there are two major criteria for choosing or adopting a model. The criteria for choosing the criteria for adopting a model. Which model? The fluid particle reaction model. The fluid particle reaction model. Now, what are these criteria? Okay, number one is the model that has close representation of reality. Number one is close representation of reality. Close representation of reality. Okay, one of the criteria or a criterion, okay, for adopting a model. A good model must have a close representation of reality. A close representation of reality. Then the second criterion, which is one of the criteria for adopting a fluid particle reaction model, is not having the model that does not having too many mathematical complexities. Not having too many mathematical complexities. Okay. Now, for a model to be generally accepted, okay, it must have a close representation of what is actually happening, that is reality. And then, in addition to representing reality very well, okay, its mathematical representation must not be too complex. Must not be too complex. Now, we have two models, okay, that their mathematical representation has little complexity. They are not too what? They are not too complex. Now, these two predominant models are number one, the models for non-catalytic. Okay, let's write it. Model non-catalytic heterogeneous reaction model are number one, the progressive conversion model. The progressive conversion model. Number two is the shrinking unreacted core model. Okay. Now this is the acronym is PCM. The acronym for this is SCM. Okay. Now these are the two predominant models for non-catalytic heterogeneous reaction. Okay, for non-catalytic heterogeneous reaction. Okay, that is for fluid reacting with solid to give products. Remember, we are concerned with solid products. Solid products. Now, what is progressive conversion model all about? Now, basically, progressive conversion model (PCM). In progressive conversion model, which is PCM, solid reactant is converted continuously and progressively throughout the solid reactant particle. The solid material is converted continuously and progressively. Now, this is it. For PCM, for PCM, for PCM, that is progressive conversion model, we visualize that the fluid, okay, entered the solid particle, okay, entered the solid particle, diffusing throughout the solid particle, and then the reaction between the fluid and the solid was continuous throughout the solid particle, happening at the same time but at different rate. I'll come again. For PCM, that is progressive conversion model, we visualize that the fluid reactant, okay, the reactant, that is the fluid, okay, entered the solid, okay, diffusing throughout the solid, and then started to transform or starts transforming the solid continuously, progressively, continuously but progressively. When we talk about progressively, we mean at different rates throughout the what? The solid particle. Okay, it's very simple. We assume or we visualize a gas or liquid that is a fluid, okay, entering, okay, solid mass, the solid reactant, okay, and then the reaction happening continuously at the same time throughout the whole solid, okay, but at different rates. That is what the concept of PCM, that is what PCM, which is the progressive conversion model, that's what it is all about. Okay. Now, when we talk about the shrinking unreacted core model or simply the shrinking core model, the concept of shrinking core model is that at any time during the reaction process that there is an unreacted core that keeps shrinking throughout the reaction. I will come again. For shrinking unreacted core model or shrinking core model, the concept is that at any time during the reaction, that is at any time where the fluid is reacting with the solid to transform it into the product, which is solid product. That's our concern. Okay? At any time this thing is happening, okay, that there is a presence of unreacted core. There is a presence of unreacted portion of the solid that keeps reducing in size, that keeps shrinking throughout the process, throughout the reaction process. which is against what PCM stands for. For PCM, there is no unreacted core anywhere. There is no unreacted portion of the solid. All the solid part, all the solid portion, everything about the solid is undergoing the reaction at the same time, continuously, but at different rates. But for shrinking core, all the parts don't undergo the reaction. Okay, at any time, provided that the reaction process have not elapsed. Okay, at any time when the reaction uh, is taking place, there is unreacted core which keeps reducing in size. Okay, which keeps reducing in size until the reaction end, where the unreacted core does what? Is exhausted, and then there's nothing to react again, which makes the reaction to come towards completion. Okay, that is what SCM. SCM. Okay. I don't know if you have any question, you can drop it there. Now, when we compare PCM and SCM, you will notice that when looked at closely, shrinking core model closely represents what happens in reality more than progressive conversion model. We are not saying that there is nothing like progressive conversion model, that it can't take place. If it can't take place, then its concept might not be beaten, something like that. But in life, or in real life, in reality, shrinking unreacted core model represent what actually happens in real life more than the what progressive conversion model. Now, assuming under the criteria, remember that there must be close representation of reality, and then the model per se should not have too many mathematical complexities. Assuming that everything is being equal, or all of that things being equal, that is, assuming that these two model has does not have these two model have or does not have too many mathematical complexities. Okay, now you will notice, or you will agree with me, that the shrinking unreacted core model will be chosen as the best model. Okay, so because in as much as both of them does not have many mathematical complexities, but one represents reality more. How does shrinking unreacted core represent reality? Now, in the burning of coal, you will notice that fire is a chemical reaction. You see, notice that the fire does not burn the coal, okay, but the inner portion of the coal at the same time. No, it does not. It starts from without, outside the coal, and then as the flaking ash, okay, as the flaking ash is dropping, it gets to consume more and more of the coal. Assuming another one is the one, let's bring it home. In the burning of wood, okay, for some of us that grew up in the village, okay, so we use firewood to cook. Now, in the burning of wood, you will notice that the fire starts from outside the wood, and then the flaking ash keeps dropping, exposing the unreacted core, which is now the wood, part of the wood that is yet to what, be consumed by fire, something like that. Okay, so you see that burning of coal, burning of wood, burning of briquettes, and burning of tight, or what's it called? Newspaper. If you squeeze newspaper, okay, if you squeeze it into a very tight ball, something like that, okay, the burning, all of them favors what? Shrinking core model. Shrinking core model. All of them favors what? Shrinking core model. So you will notice that shrinking core model represents reality more. You get? Represent reality more. Okay, so for that reason, you will notice that or you will agree with me that this will fly above this. Okay, so that is the reason why in our derivation we are adopting SCM. We are adopting the shrinking unreacted core model. So in our next video, we will be looking at SCM proper. Our derivation will be based on this chemical reaction equation, that is the fluid reacting with solid to give solid products. Okay, and this solid products, okay, the formation of this solid product is following shrinking unreacted core model. That is, this solid, okay, this solid reacting with the fluid. Fluid started reacting or started transforming the solid from without, okay, outside the solid, and then the reaction now progressed okay, to the inner core of the what of the solid. So we are adopting what? Shrinking unreacted core. We are adopting this particular model. We are adopting this particular model. In addition to that, we are adopting a non-flaking ash impurity. Okay, we are assuming, okay, that our impurity, that is the leftover from the reaction, is in form of a non-flaking ash. What does that mean? That they don't detach from the unreacted core. They don't detach from the unreacted core. Okay. Now, since they don't detach, that means our solid is what has unchanging size. Has unchanging size. So three things I want you to notice this. Number one is that in the derivation process, okay, we'll be working with this equation, and then adopting this model and assuming on changing size. Okay, we're working with this, assuming this model, and working with what? On changing size. Thank you very much. See you in the next class.